workshop in geometric topology. You are in room 3, in case you're wondering where you're at. You'll be seeing the talks in room 3, contributed session 3. Our first speaker today is Thomas Weighill from UNC Greensboro, and he's speaking on the coarse geometry of hyperspaces. So go ahead.
Thanks very much, and thanks for the opportunity to talk a little bit here about some joint work with 2 collaborators, Takamitsu Yamauchi and Nicol Zava, that we did. So the basic context that we wanted to understand for this work was sort of very simple setup. We have a metric space, X, and sometimes there'll have to be some extra restrictions on this X, but most of the time it's just a metric space, nothing particularly going on. And H of X is some subset of the set of all subsets of that space. So I'll talk a little bit later about what the metric here is, what the geometry here is, but the basic idea is, how do we understand the space of all subsets of an ambient metric space? So I'll sometimes refer to this as the ambient metric space. And there are many questions you might want to ask about such a subspace. The one that I'm mostly interested in is the question of trying to embed the subspace into something else. So taking, whatever your favorite collection of subsets is and their geometry and embedding them suitably, I'll explain all the details at some point, into some useful space. Usually what you want here is some kind of linear space. So you want a vector space, or more specifically, maybe a Hilbert space or something like that, in order for you to be able to do linear algebra with this stuff. Now, there are many reasons why you might care about this. There are many reasons, for example, to care about the set of all normal subgroups of a group in geometric group theory, or things like this, or consider, I don't know, there are people who care about configuration spaces, or all the closed subsets of a topological space. I wanted to show 2 examples where this kind of thinking about trying to understand the geometry of subsets comes up in my sort of very applied work, and where it actually is super relevant. So my favorite applied subject right now is redistricting, which seems fairly far from this topic. And I'm not going to say a lot about it. Feel free to ask me about it if you want to, but basically I want to study maps that look like this, congressional districts inside a state, and answer some basic questions about them using data science and statistics and math. And the reason that this involves subsets is for the simple reason that, congressional districts are subsets. They are a subset, in this case, of North Carolina. And understanding the distance between them, or understanding how I can maybe embed the space of all possible districts into something useful, this turns out to be a kind of important problem. We've recently completed a project where we had to compute barycenters of redistricting plans. So the geometry kind of comes in pretty quickly. Another place where subsets matter and the geometry of subsets is persistence diagrams. So there've been a couple of talks in this conference, I think, on TDA. I saw one yesterday. I'm not going to go into detail on what TDA is, except to say that, you take some kind of data, you do some thickening or filtering or thresholding or whatever, and you end up with something called a persistence diagram. And this persistence diagram is supposed to reflect the underlying topology of whatever data you had. But the thing I want to note is that this persistence diagram, as you can see here, it's a subset of the plane. All the red dots, basically. So that it's a subset of the plane. And so, doing machine learning on persistence diagrams basically comes down to understanding how subsets of the plane interact, what their distance between each other is, what an average is, what a sum is, these kind of things. And this sort of is a well-trodden path in TDA. I've got 3 particular examples of ways of taking, your space of persistence diagrams. So this is really the space of all persistence diagrams, and trying to put them into a vector space structure here on the right. There are very different approaches, and they have their sort of pros and cons. So that's just 2 examples of why in the applied sciences, you might care about the space of all subsets. So going back to sort of our abstract context, so I can lead up to our main result, what we're looking at is X is again going to be a metric space. And I'm mainly going to be interested, although I'll have results about more restrictive setups, but the main thing of interest is the set of all finite subsets. So this is the set of all finite subsets of space X. And the metric I want to put on them is the Hausdorff metric. So, there are possibly a number of different choices you could make here, but the Hausdorff metric seems extremely natural. It's for finite subsets, it's defined, which is nice. What is it? Well, I'll quickly draw a picture if you haven't seen it before. If you've got some space A and you've got some space B, some subset B, you ask two questions. You ask, what's the radius around B that encapsulates A? So maybe it's this radius here. And you ask, what's the radius around A that encapsulates B? Maybe it's this radius here. And you ask for the maximum of those two, right? And then you basically, the maximum of those two, that's the measure of how far apart these subsets are. So how much does it take for one subset to subsume the other one? Okay. And the type of, so this is the space I'm interested in. The type of embedding I'm interested in is the weakest one you can probably come up with in terms of an embedding of any kind of geometric sense. And that is, I want to take my space, in this case, it'll probably be h of x, but in this setup, I have x and y, for example, and I want to do what's called a coarse embedding. A coarse embedding is just an embedding where I have some control over the distortion that's taking place in the two distances. In particular, if I have 2 points and I map them over, if I know something about their distance, I can find upper bounds and lower bounds for this. So if I know that this is, say, less than r, then there's some s, depends only on r, that I know that this distance is less than s. And if I know that this distance is lower bounded by r prime, then I can say, okay, this is lower bounded by s prime or something like that, right? So there's some control over how much I can squish distances and take it apart. So an example of this might be a bi-Lipschitz embedding. So if you know what a bi-Lipschitz embedding is, that's a special case of this. This is kind of like a coarsification of it. It's basically the weakest version you can come up with. Now, coarse embeddings matter a lot for two reasons. One, it's a measure of how good an embedding is. And if you have a good embedding between a space and some linear space, you can do machine learning on it. You can do kernel tricks. You can do take means and stuff like that. But it also comes up in the sort of the abstract things that I'm interested in, because there's this famous result of Guliang Yu in 2000, which says that if you have a group with a word metric, then embeddability in Hilbert space implies the Novikov conjecture for manifolds with that fundamental group. And this sort of is part of a long line of inquiry into what kind of embedding properties lead to what kind of sort of good coarse behavior. And it has connections to all kinds of conjectures. There's this kind of central spine of coarse properties related to embedding in Hilbert space, which more or less follow sort of how Guliang Yu was able to prove the Novikov conjecture for various classes of groups. The sort of most restrictive thing in that hierarchy is this notion of finite asymptotic dimension, which I might define later on a slide, but it's not extremely important for this. Finite asymptotic dimension implies property A. Property A, this is due to U. Again, I won't really describe what that is, because the only reason property A was originally introduced was as something which implies coarse embeddability, right? It was a way to check there's something embedded in Hilbert space. Now, since then, there's some exotic examples which differentiate property A from coarse embedding in Hilbert space. But mainly, it's the thing you want to prove embedding in Hilbert space. And coarse embedding in Hilbert space implies this coarse-Baum-Cohn conjecture, which is the thing that gets you the Novikov conjecture via this principle of descent. So there's this kind of hierarchy, and sort of in between these two, and sort of in between, maybe between finite asymptotic dimension property A, there's a whole industry of various different properties you might consider. Asymptotic property C, decomposition complexity of various flavors that are all in there. But I'll be focusing mostly just on these. So here's the main result that we got. If you have a metric space that, and here's a condition I'm going to have to explain, contains a sequence of long intervals coarsely. It's a fairly mild condition, which I will define in just a minute. Then the set of all, remember this is finite subsets. So this is finite subsets does not embed into Hilbert space. So in other words, it fails even the weakest of this hierarchy over here. And by long intervals, what we mean is, well, we first define what a sequence of long intervals is. A sequence of long intervals is just what this picture is. It's a set of intervals in the plane that are getting increasingly longer, but also getting further and further apart from one another, right? And the spacing out process, this is very common in sort of coarse geometry type settings, because you basically want them to be far enough apart they don't interfere. And we say that a space contains a sequence of long intervals if there's a coarse embedding from such a sequence of long lines into your space, right? So it contains it coarsely. So examples are any geodesic space you can do this with. You can just take increasingly long geodesics and take pieces of them sufficiently far out. You will find these long lines. So an example is any unbounded geodesic space. A Zn is not geodesic, but it's coarsely equivalent. It's quasi-isometric to Rn, so that's good enough. A non-example, well, that might be something that isn't very connected at all, even at scale. So like in very, very spaced apart numbers, like the squares, and considering them with the natural sort of distance that they come with. We originally thought that it might be the case that if you are not asymptotic dimension 0, in other words, if you are actually unbounded and you're connected at some distance, you can hop from one point to another by some distance, then you had to contain such a sequence. We managed to find a fairly complicated non-example, which shows that this is not necessarily be the case. And so it's a locally finite one connected metric space, which doesn't contain long intervals. I won't be sketching that just because it's a little bit annoying and complicated. You can try for yourself what the obstacles are to trying to construct such a space. And if you follow that enough, you might come up with our example. So how does our non-embeddability work? I'll say a little bit about the proof, because the proof's actually really, really nice and easy. And it sort of has connections to other ways people have proved similar analogous results. The basic idea is to take this Cartesian product here for whatever value of n and m you like of intervals with the soup metric and to try and embed it. And it's kind of a fun thing to show by example. So for example, if m is, let's say 0 to 10, so 0 to 10, and let's say n is 4, I want to embed this 4 tuple as a subset of my long lines. Well, I just do it coordinate-wise. I find 2, I find 1, I find 4, and I find 6, and that's my embedding. I've embedded this tuple as a set of points along these lines. And now if I do it for a different tuple, let's say 3, 1, 1, and 4, right? It's not too hard to believe that the distance between those tuples is related to the Hausdorff distance between these points. Maybe there are some issues with them interfering with each other, but eventually they get spaced out far enough that it's not really important, and that it comes down to the distance is basically the Hausdorff distance. So I can embed these sort of hypercubes, these 0 to m, 0m to the n, and there's this full of sort of well-known result, which is a nice exercise for undergraduates who had seen metric spaces for the first time, which is that every metric space embeds into a soup metric space with this Kuratowski embedding. And it's not hard to check that if you just think about it enough, every finite metric space embeds sort of in a finite soup space like this. It embeds in the interval diameter to diameter to the power y, right? And so it's just the Kuratowski embedding. So the result is that if a metric space contains a sequence of long intervals, something very, very bad is true. That is that the space actually contains a coarse disjoint union of any sequence of finite metric spaces. So you can put take your favorite set of metric spaces, all of them finite, but an infinite family, and you can kind of countable infinite family, you can space them out throughout your space. So in particular, you can take a sequence of expander graphs or your favorite set of examples that don't embed into Hilbert space properly, and you can just put them inside this hyperspace. And there's just no way that the space that you're interested in, this space of finite subsets, can embed into Hilbert space. Right. And so this is kind of similar to proofs in a different realm, which is in persistent homology in TDA, where we have also this question of, can I embed my persistence diagrams into Hilbert space with bounded distortion? And the answer is known to be no for a large number of examples. I just put here what's known. So I won't explain what the P Wasserstein metric is, but sort of our result is closest to the so-called infinity Wasserstein metric. This is also sometimes called the bottleneck distance. And for p greater than 2, it's known that you can't embed into Hilbert space. And there are some very nice overlaps between the techniques that we use and the techniques used there. So it's kind of a similar strategy. You basically focus on embedding nasty things into that space using kind of a Kuratowski trick. It's unknown, by the way, for 2 and 1. So that's still open as far as I know. Now, can we get any positive results? Well, if we restrict ourselves to subsets with at most k elements, we can get somewhere. This was something that we thought we came up with, but it turns out that the chain of results you need is kind of already in the literature. And so at least for property A and embeddability, they're already there. So we just kind of put it all together and then added some more extra results along the same lines. The main trick is to take this map, the natural map that goes from k tuples, like ordered k tuples, to subsets, which just forgets. It just takes a tuple and it forgets that it was a tuple and treats it as a subset. And this map turns out to have a very nice property in coarse geometry called coarsely n to 1. What does coarsely n to 1 means? Well, an n to 1 map should have fibers of cardinality n. A coarsely n to 1 map means that if I have a ball of radius r, then I look at its pre-image, whatever that is, it should be covered by n balls of radius s, where s is somehow dependent on r. So there's an s of r for each of these balls. So it's kind of like, okay, it's not really n to 1, it's not really n points to 1, but it's like n small sets to 1 small set kind of thing. And these are incredibly useful. For example, they preserve a bunch of properties, such as if you have a surjective map, which is coarsely n to 1, there's also Bornologous. You can ignore that word, it just means the appropriate kind of continuity. Then if X has property A, then so does Y, right? And remember, property A is just this nice amenability type property that implies embeddability in Hilbert space. And we also have this fact that property A is preserved by products. I'm not sure who to credit this to, but it's probably in Rufus Willett's notes somewhere if you want to see. And so there's this observation that, again, we made, but was actually made before us and approved by Dranishnikov and Zavishny, which is that this map, this forgetful map, is coarsely n to the n to 1. This is actually kind of a fun exercise to check, that it's at least coarsely n to the n to 1. So bringing it all together, how does it go? Well, you have X, which has property A. You say, well, I know that X to the K has property A. I know there's this nice map to the space of k point sets, right? And I know that this has property A implies that has property A implies that has property A. And in property A implies coarse embeddability. So we get that if you have an ambient space with property A, and this is most spaces. For example, the only finitely generated groups that don't have property A tend to be these horrible Gromov monster things. A lot of spaces of property A, in particular, anything with finite asymptotic dimension has it. So it's not a strong requirement. Then you know that your finite thing is going to embed. This argument leads to a dichotomy between asymptotic dimension. So if your ambient space has asymptotic dimension 0, then it's not so hard to show that this k-point set has to have asymptotic dimension 0. Sorry, not k-point sets. All finite subsets actually has asymptotic dimension 0. On the other hand, if it's at all positive, a very similar argument using these coarsely n to 1 maps works like this to give you that it has to be infinitely dimensional. So in other words, the minute you have any positive dimension at all, your hyperspace is very badly behaved. We're not able to prove the same thing for embeddability in Hilbert space, but I won't mention too much about that. And there's an analog in persistence diagrams where Miata and Verk showed that the space of persistence diagrams with at most endpoints coarsely embeds into Hilbert space, and it uses exactly the same idea with these coarsely n to 1 maps, which is nice. Finally, I'll mention that there is an analog here in optimal transport in computational geometry. So if you wanted to generalize subsets, the natural way to generalize subsets is to generalize them to distributions. And the natural way to talk about this is the space of distributions. And I just wanted to mention that we also have, that we don't have this, but it was proven by these 3 people that you can't embed spaces of distributions, at least not when you have 3 dimensions here and p greater than 1. You can't embed that but it's still open with the distributions on our squared embed, which is an extremely relevant example for the two things I mentioned, redistricting and persistence. So I'm super interested to see if someone eventually solves this distributional version of the embeddability problem. And I'll end there and point you to the paper.
Okay, are there questions for the speaker?
I wanted to ask, is there any way to tell whether you can embed it into a separable Hilbert space or not?
Yes, so these are all separable Hilbert spaces, I think.
Okay.
Yes, so the thing is, you might as well work with a countable discrete version of your space. Is that right? I think for all these results, so for the property A results, I lied a little bit, I think, because I think you need the space to be bounded geometry, and that gives you that the space is coarsely equivalent to something countable. And once you have that, you can choose the Hilbert space to be separable.
Thank you.
Thanks for the question.
Yes, if you have a question, just unmute yourself and jump in and ask.
So I guess I'm just curious to ask about if you wanted to mention something about the more about the application you said at the beginning, the redistricting. Because why not?
Yeah.
Sounds cool.
I mean, I wouldn't say that what we did here applies directly.
Sure.
I feel like I'm kind of working the pasta noodle from both ends and hoping to meet in the middle. But basically, in the redistricting application, what we were interested in is, given a ton of districts or given a bunch of plans, can you find an average? And the reason that the geometry matters is that the space of all plans suitably defined is extremely positively curved. So you may know that if you have a non-positively curved space, then you can find unique barycenters in most cases. In this case, you can't, and you can prove sort of rigorously that the curvature isn't even bounded from above. So that kind of throws away a lot of hope for finding barycenters, for doing sort of standard machine learning stuff on these spaces, and also makes it very hard to embed what you're talking about. So depending on which version of the space you're working with, is also extremely hard to embed. So we had to come up with slightly different ways of doing things, based on not quite first principles, but based on adapting kind of approximation algorithms to find the average plan for North Carolina from a sea of 1,000 plans. But in general, it leads to these questions of, if you have a data set where the underlying data points are shapes, how do you feed that to the computer in a way that it wants to do things? And I think that question is becoming increasingly important in applications.
Sure. I was just curious if there's something analogous. I've seen something in numerical analysis where basically, if you're doing floating point arithmetic, to only so many decimal places, maybe for your theorem application, you didn't actually need it to be a perfect metric space, like an exact, completeness or limits. It just needs to be kind of up to some epsilon, some sufficient epsilon to however precise the numbers are. Does this field have something analogous, or kind of just only needing something to not actually be like a perfect metric or perfect Hilbert space, but just kind of up to some degree of accuracy for the computer? Or is the theory still done in the full, pure sense?
Good question. I mean, in some sense, we are trying to do things approximately, in the sense that we're embedding into a true Hilbert space, but the embedding is bad. It might not even, it distorts distances all over the place. But the kind of guarantee you want is you at least want a cap on that distortion. So you want to be able to say, I had these two things that were 1 unit apart. They can't possibly more than 50 units apart over here. And 50 it sounds really bad, but at least it's no more. So the goal usually is, and embedding into a Hilbert space, you can think of as embedding, but you can also think of as trying to put a inner product on your original space a little bit. And it's basically saying that inner product is not quite so terrible as it could be. And sort of the numerics, yeah, so that's how we sort of talk about approximation, right? We want it to be a low distortion approximate embedding into some other space. And in that other space, we can do exact computations. So that's kind of the philosophy behind this.
Very good. Thank you.
Yeah, thanks for very good questions.
Nothing would be like chaotic here.
I'm not sure what chaotic would mean. I mean, yeah, I would have to think more about that to think if there's any chaos.
I mean, it seems like if maps are linear in the end, then it shouldn't be a problem, right?
Yeah, I guess chaos maybe enters the situation where you have to approximate these districts, and you're always scared that the finer and finer your resolution, the worse everything gets. That might be a nightmare, but I haven't run into that yet, so I don't think.
Sure. Thank you.
Anyone else? Otherwise, let's thank the speaker. You can either use your electronic reaction or actually clap.